With version 1.0 of our preservation replication implementation, say that fast, we now have binaries flowing through an asynchronous architecture from our large set of mounted drives locally at Stanford to AWS Cloud. This is the same diagram that we've displayed previously in some of our demos, now implemented fully and working in production. So a few things have changed. We have to deal with zip parts and not just zips, because sometimes making zips of 300, 400 gigabyte objects or larger, up to several terabytes, is problematic. So we use built-in technology of zip to segment those into more manageable sizes. Other than that, everything works the same as we presented previously. The important part is here on the lower right, where the actual delivery happens. All the authentication for a given endpoint, in this case AWS West, is encapsulated here, and the rest of the application doesn't have to know or care. And therefore, when we scale out to other endpoints, say AWS East or a different S3 provider, all we have to build is the worker and the environment for that worker, instead of doing a bunch of tooling in the application. All right, here I'm connected to our production system, and you can see in our logs how jobs have been enqueued for delivery, enqueued here, and then performed in different capacities. S3 West is the one that we're currently concerned with most. And you can see it's delivering for a Druid, which is just an identifier, a version of that Druid, and then a part of or a zip file made from it. There's some other metadata that will help us later if we ever have to reconstitute things or put things back together. It says size, parts count, but this is where the action is. We can go ahead and queue things up directly. Here I have a preserved object. So if we wanted to queue this object up, it's represented in our database already for replication again, or for the first time. We have the identifier, the Druid. We have the version, currently 7. And with those two things, we can hand off to a job that will do it. And there it's enqueued. Back here, we can see that it's enqueued this job. It's going to go ahead and process the various things related to this job. And it started working right away. The result of that was pushed on to the next part of the diagram. And eventually that will make it through to the actual delivery worker. With this, we've been able to, without much tuning on one machine with a handful of workers, we've been able to move at peak roughly 1 terabyte per hour, which is impressive considering that it's coming not from local storage, and we haven't done a ton of optimization. When we throw additional horizontally scaled workers at this on other machines, we would expect to be able to burn through our backlog. That obviates the need for any snowball-style transportation device or more complicated workarounds. It's vindicated, and what we're going to carry forward. The nice thing is this isn't any different than what we would use once we have the backlog pushed through, and we're only interested in replicating novel versions. The same architecture will be used, maybe not with the same amount of resources, but nothing else has to change. Here's our rescue interface, which is the back end for our asynchronous jobs. You can see that it's actually burned through all the things that we enqueued previously. Let me enlarge this font. Right now, we're looking at 17,000 things that are waiting to be delivered. So that's how many things we queued up through various attempts. We're adding this fourth box, which will add new workers. So it'd be interesting to recheck our stats and see if we can't get even faster. 71,000 total jobs processed in this series, and with those 17,000 remaining. Thanks for tuning in. Overall architecture, this will probably not change between the conclusion of this work cycle and now. Thank you very much, and we'll catch you next time.